We were discussing electron correlation, and in the last few classes we have discussed what is electron correlation is. Whatever is missing in the Hartree-Fock picture is called the electron correlation, and we have understood various ways of including electron correlation. We have seen MP2, we have seen configuration interaction. In the MP2 method, the electron correlation is included perturbatively, and in the configuration interaction, the electron correlation is included variationally. And we have understood what are their strong points and what are their weak points. We have known about size extensivity, size consistency and strict separability. So, now we come to the theory couple cluster, which is neither variational and nor perturbational. From a personal point of view, this is my favorite theory because this is where I work on. So, in the couple cluster, the exact wave function is generated by an exponential operator acting on the Hartree-Fock or the reference determinant. This Hartree-Fock determinant, let me go to the pointer. So, this Hartree-Fock is the 0th order reference wave function for this couple cluster, and this exponential t acts on this to generate the couple cluster wave function. Now, this 0th order reference function may not be Hartree-Fock, it can be any single reference determinant. Some people try DFT determinants to do that, but for all practical purposes Hartree-Fock is the best choice because we know that Hartree-Fock is the best single determinant possible. So, whatever is missing in the Hartree-Fock is small, and that can be recovered by using this exponential operator. That advantage will not be there if we use some other single determinant other than Hartree-Fock. So, because it is exponential t, I can expand this one in the exponential series. So, you can see T1, T2, T1 square, and all this will go on, where this T1, T2 these are cluster operator. So, T1 is one body cluster operator, T2 is two body cluster operator, three body cluster operator, so on. And for n body cluster operator, this part, the first part, the small t is called the amplitude, and this part is actually what it generates wave function. We will come into what this is within the curly bracket. So, for the one body operator this will look like this, for the two body operator T2 will look like this, three body operator it will look like this, and this will go up to n body operator where n is the number of electron in the system. Now, this what is within this curly brackets is second quantized creation and annihilation operator. Up to most of the quantum mechanics we have done up to now, we have seen in terms of first quantization in terms of operator, whereas in the second quantization the same picture can be generated by using creation and annihilation operators. This is outside the scope of the present scope, but if you want to know more about this creation annihilation operator and couple cluster and more details about these theories, there is an NPTEL course running on which is known as many body methods in quantum chemistry. So, you can check it out. Now, what is so if I look more closely at the structure of the T operator, I have shown that there are two parts. So, this actually acts on the Hartree-Fock determinant and generate all the possible excited determinant. That is what we discussed, that is what the correlation means. I excite electron from the Hartree-Fock. So, that is what it happens is that my electron now gets more space to move around in the if I think the determinant as a space for electrons. So, in the Hartree-Fock picture there is only one determinant where the electrons are localized. Localization may not be a correct word, one determinant where the electrons are there. In case of electron correlation, what happens? Many more determinants are generated. So, now electrons can avoid each other in a much better way. So, their repulsion between them can be minimized. Now, this cluster operator has two parts. The first part is the cluster amplitude and the second part is the creation annihilation operator. So, this creation annihilation operator acts on these Hartree-Fock determinants to generate the excited determinants, and these T amplitudes, this small t is called amplitudes or sometimes they are called ansage also. So, they give the weightage of this generated excited determinant into the final wave function. Now, what we have seen up to now, the equations were solved perturbationally and variationally. In this case of couple cluster, this is the couple cluster Schrodinger equation and this is solved, this is the equation for the energy and this is the equation for the amplitudes. So, in this case the energy and the amplitudes equations are solved by projection, And remember, because it's an exponential operator, the projection and variation is not same, whereas in the case of configuration interaction, the variation, because it's a linear operator, the variation and projection actually leads to same answer. Now, of course, we cannot take up to n body operator. If we take up to n body operator, actually it will lead to a full Ci energy, and so that means if I see the eigenfunction of this h bar, they will be same as the eigenfunction of h, that is the original Hamiltonian, and the reason is very straightforward, because h bar and h is related by a similarity transformation, and if we know that if two operators are related by similarity transformation, they have a same eigenvalue spectrum. So, if I take up to n body operator, that's another way of reaching full Ci. So, it will have a same energy as the full Ci, the wave function may not be same. Now, for practical application, one need to truncate, but before we truncate the T operators, the n body T operators, one distinct advantage in this case, although this is an exponential series, so in principle I can have higher powers of T, but because there is a commutator with the Hamiltonian and the T amplitudes commute among each other, so this series truncated at the fifth term. So, the Hamiltonian at most can have 4 commutators with the T operator, beyond that rest of the contribution will be anyway 0. So, there is a natural truncation, and this terms in this series can be evaluated using Wick's theorem. So, this is one natural truncation, then we will truncate the n body cluster operator using some logic, but before going that, let us see what is the advantage of coupled cluster, why people tell that coupled cluster is an exact theory. Remember the Ci picture again. So, what happens in the Ci picture? There was an Hartree-Fock determinant, and we generate singly excited determinant out of it, doubly excited determinant out of it, triply excited determinant out of it, quadruply excited determinant out of it. And this is my Ci wave function. So, where this small Ci is a linear operator, and this form is given like this. So, it is very similar to the coupled cluster T operator, and this is my coupled cluster wave function, where my form of the operator is exponential, and the T actually looks very similar to the C. Now, if I truncate it to the only 1 and 2 body excitation operator, CISD and CCSD. So, what happens if I restrict my operators to 2 body operators? In the Ci picture, I can only generate singly excited configuration and doubly excited configuration. I cannot generate triply and quadruply excited configuration, because my Ci operator is truncated up to double excitation. What happens in the case of coupled cluster? Of course, the T1, the small amplitude will give me the weightage of the singly excited configuration, like the Ci. For doubly, I can generate the doubly excited configuration in 2 ways. One is by 2 body operator, and second is by operating the 1 body operator excitation operator twice. So, I can directly have 2 electron excitation, or I can have 1 electron excitation sequentially. Now, for CISD, you cannot go beyond the singles and double structure. What happens in the coupled cluster, although your operator is truncated up to singles and doubles, I can generate configuration which is triply excited with respect to Hartree-Fock by operating this T1 operator. This is the amplitude. So, T1 operator 3 times, where the amplitude will be given by T1 cube, or I can first operate the T2, which amplitude is given by this T1. So, capital T is the operator, small t is the amplitude. So, I can first operate the T2 and then T1. So, it will give me a triply excited configuration. Similarly, for quadruples, I can operate the T1 4 times, or I can operate T2 once and then T1 2 times, or I can operate the T2 operator twice. So, that will give me the quadruply excited configuration. That means, only with the knowledge of single and double excitation operator in the coupled cluster, I can actually span a part of the triply and quadruply excited determinant, which is not possible in the case of Ci, because Ci is a linear operator. So, I cannot have the square or cube terms. So, that is why for the same level of truncation, coupled cluster is much more accurate than a Ci. There are additional advantages to it, and that additional advantages comes in the form of size extensivity. Remember, size extensivity is actually related to the scaling of the energy with respect to the number of electrons. Now, to have the proper scaling, if I have two systems, let us say stretched at the infinite limit, my cluster operator should be, or my Ci operator should be the sum. And if I consider my Hartree-Fock wave function separates very correctly, so I can write them as a product of, if I have an xy fragment separated infinite distance, so I can write the product, the Hartree-Fock wave function at the product of the individual Hartree-Fock wave function of x and y. In the case of coupled cluster, because my exponential operator is additive, so it can correctly the wave function can correctly separate it. So I can write the e to the power tx plus ty, and then I can write it as an individual two multiplicative form of the wave function. Whereas in the case of Ci, even when my Hartree-Fock wave function is multiplicatively separable, my total wave function is not multiplicatively separable. So the problem is that the total energy of the fragment will not be summation of the individual energy even at the infinite distance for the case of Ci, whereas for the coupled cluster, my individual energy will be the sum of the coupled cluster energy of fragment x and fragment y. So this will lead to problems of size extensivity, separability in the case of Ci, whereas in the case of coupled cluster, this problem will not be there. Now, of course, for all practical applications, we need to truncate, but remember whatever we have shown in the previous slide, that is applicable for any arbitrary order of truncation of the cluster operator. Does not matter I truncate at 1 body, 2 body, 3 body, 4 body, this rules will hold true. Whereas for Ci, the correct separability will only come when you go to full Ci wave function. For any truncated limit, this will not be true. So for all practical application, one need to truncate the coupled cluster operators. Like the Ci, the coupled clusters operators are approximated up to a certain excitation levels. So in the CCS, what is called a coupled cluster singles, the wave function contains only up to single excitation. In the CCSD, the coupled cluster singles and doubles, the wave function include excitation operator up to single and double excitation, and it scale into the 6th power of the basis set. And in CCSD-T, where you have singles, doubles and triples, the wave function contains 1 body, 2 body and 3 body operators, scales as n to the power 8. You can go to CCSD-TQ, singles, doubles, triples, quadruples. The wave function contains up to singles, doubles, triples and quadruple excitation. Among them, the coupled cluster single doubles is most widely used because it is n to the power 6 scaling. Remember, when I say most widely used, even for n to the power 6 scaling, it is very difficult to perform calculation beyond 10 atoms unless you have access to massively parallel supercomputers or use some additional approximation. So up to 10 atoms CCSD may be still possible. CCSD-T and CCSD-TQ, it is very difficult to do beyond diatomic or triatomic molecules. Diatomic and triatomic molecules, because they have high symmetry, you can maybe do CCSD-T. CCSD-T may be possible to do for triatomic. CCSD-TQ, which is n to the power 10 scaling, and not only the computational scaling, it also has a huge storage requirements to store this amplitude. So it is practically impossible to do this beyond diatomic and triatomic molecules. CCS does not account for electron correlation due to Brillouin's theorem, and that is why they are very similar to configuration interaction singles. Advantage is that in any of the truncated level, unlike the case in Ci, CCSD does not suffer from size extensivity problem. And to show that, we will again go back to our example of helium systems, and we will do calculations, and we will see that if I have this helium 7 cluster, if I multiply the energy of the one atom by 7, and if I do it by calculating actually the energy of the cluster at the MP2 level, I have seen that multiplying by 7 or actually calculating give you same energy, whereas in the case of CISD it was not true. So there was size extensivity error. In the case of CCSD, this will be an homework problem to see if the energy of the coupled cluster for the He7 cluster is same as if I multiply them of the energy of the one atom with the number 7. So it will be a good idea at this point is to do a calculation on a helium atom, and maybe I will be able to show you something how to read the output file. So let us go to this one. Let me open Notepad. So the ORCA, the line start with an exclamation mark. If I want to do couple cluster, I will write it CCSD, couple cluster singles, doubles. I need to give the basis set is def to let me increase the view a little bit. It's an atom. For helium, of course, the Cartesian coordinate does not really matter. So I can give it 0, 0, 0 because it's an atom. The molecule it would have been an issue. And let's save it. Let me make another folder called HE and let's save as HECCSD. We have to make sure that the extension is .inp, so you have to change the .text to make it .inp, and let me now go back. Open in terminal. So my calculation is complete. Let me open the output file. Again, usual stuff, method, basis set, the Hartree-Fock calculation will be of course performed. So after the Hartree-Fock, what is done is that, remember helium is two electronic system for CISD or CCSD. In this case is same as full CI, but that's not the case for the helium-7 cluster. So after my Hartree-Fock is done, what it will do is that it will try to transform the integrals from the atomic orbital to molecular orbital basis, and it says it's 1x how the memories will be used. So by default it takes 256 MB of RAM, you can change it, and it will generate all the possible integrals, it will generate the Fock operator, and here it does the AO to MO integral transformation, which scales as n to the power 5, less than the couple cluster step, but this step has a very bad prefactor. So sometimes this can take a huge amount of time unless you take additional approximation, and any couple cluster actually start with an MP2 guess. So if you perform a couple cluster calculation, it will also calculate the MP2 energy, and this is how the couple cluster iterations will look like. And the system, because it's a small system in a small basis set, so it has converged within 5 iterations. Remember, in ORCA the calculations start from 0. So this is how the energy will look like. This is E0, this is E correlation, and if I add it, it will be total. And something interesting is this term is that is called a T1 diagnosis. Now T1 diagnosis is something is basically related to the norms of the singles vector, and it tells you that if your reference wave function is good enough or not. In cases where my T1 value is more than 0.02, in that case it essentially means that my couple cluster calculations are not reliable and one need to be very careful. Sometimes this T1 stick is erroneously related to multi-reference nature of the wave function, but T1 diagnostic actually is not strictly related to the multi-reference nature. T1 diagnostic only tells that my reference wave function, my Hartree-Fock orbitals are not good. So that is why the singles operators are trying to rotate this orbital. This may be due to multi-reference nature of the wave function, and this may not be the multi-reference nature of the wave function. So T1 diagnostic only says that my starting orbitals are bad, so I should be careful about interpreting my couple cluster energies. And this is where the largest amplitudes are there. You can actually calculate the population also at the couple cluster level, may not be really interesting, and this gives the relative timing, how much time is taken for each of the individual step, and at the end it will print also the dipole moments, rotational spectrum like this, and all both at the Hartree. So here you will see there are two things. So one is the case the dipole moment will be printed with the SCF density, and second one is the with the couple cluster density. So there will be two dipole moment. So generally what is printed with the couple cluster density, what is called an MDCI, that is generally more reliable. Of course, in the case of helium there is no dipole moment because it is an atom, and here it gives the sum of the individual calculation. So for SCF it has taken around slightly less than 2 seconds, whereas the MDCI module, the couple cluster module, actually has taken slightly more than 2 seconds. But one difference you will be already seeing that for with respect to the MP2, this timings, couple cluster timings are actually higher. So as we told that T1 diagnostic is a signature of a system where my starting orbitals are not good. One can try an example of ozone. Let me go to Avogadro. And make an ozone geometry, and I can run the calculation and try to see if my Avogadro is here. I run a quick optimization. I can just write a CCSD here. I can just replace the last week's O3. So I open in terminal here. This might take some time. O3.inp. So it's done. Let me open the output file. Some previous calculations were already there, so let me open it. So this is couple cluster, and if we come down a little bit more, so in this case you remember in the case of MP2 we have discussed that ozone has total 24 electrons, and among them 6 of them will be frozen and rest of them will be taken as a calculation, 18 electrons and total 9 molecular orbital. You see it has taken more iterations, total 12, 0 to 11. Now see the T1 diagnostic value, it says it is 0.04. So, this is above the acceptable limit of 0.02. So, in this case the couple cluster results are not very reliable, and ozone is a multi-reference system. So, this is expected. So, wherever you will see the values which is more than 0.02 of this T1 diagnostic value, you should treat your couple cluster results very carefully. Now, so this is up to now is couple cluster. So, this will be another homework problem for you. So, you have to do the full series for couple cluster and actually check. Now, couple cluster in the singles doubles approximation is good, but what is actually is most accurate than the normal CCSD, more accurate than the normal CCSD is CCSD parenthesis T, which is called as the gold standard of quantum chemistry. And this is the CCSD energy formula, where this U are the six-way index matrix element of the Hamiltonian between couple cluster singles and doubles amplitude and the triply excited determinants. It scales as the n to the power 7 power of the basis set. Although this n to the power 7 is non-iterative and which is much cheaper than the iterative n to the power 8 of the couple cluster singles doubles full triples. That is why CCSD parenthesis T gives a economic compromise between the couple cluster single doubles and couple cluster single doubles triple. And this can give you an accuracy up to 1 kilocalorie per mole, which is considered as the chemical accuracy, of course, when extended basis sets are used. Like any other correlation method, couple cluster is also very sensitive to the basis set, and you need to use a very large basis set to get accurate answer. One interesting thing to notice here is the denominator. So, the denominator is similar to the molar placid perturbation theory MP, where Hartree-Fock orbital energies are used as a denominator. And this actually this CCSD parenthesis T has been derived using perturbation theory only. It means that if my starting Hartree-Fock orbitals are good, then only it will be a good approximation to CCSD full triples. Cases where my Hartree-Fock orbitals are not good, if I am stretching a bond or dealing with maybe a transition metal with heavy multi-reference character, in that case the accuracy of CCSD parenthesis T will be questionable. But for closed shell systems where there is no multi-reference character, and you can see it by looking at the T1 diagnostic, if the T1 diagnostic value is less than 0.02, then CCSD parenthesis T is a good approximation. I am not saying that it is a bad approximation if my T1 diagnostic value is more than 0.02. I am saying that in that case you have to treat your results more carefully and analyze them more closely. And how good is the CCSD parenthesis T? To see that, we will again go back to the problem of the singlet triplet gap of CH2, and we will see how the singlet triplet gap improves with the using couple cluster CCSD parenthesis T. So, this will be the second homework problem from the couple cluster lecture series. So, in this discussion of electron correlation, we have talked mostly about three methods: MP2, CI and couple cluster, and what we have discussed is that couple cluster is the most accurate of the method. Even in the truncated format, it does not have the problem of size extensivity. Remember, size consistency problem can be still there if Hartree-Fock wave function is not size consistent. But CCSD parenthesis T actually is considered as the gold standard of quantum chemistry, and it is desirable if possible to do this calculation. But the problem is that beyond 10 atom system, it becomes really difficult to perform this calculation in an extended basis set. So, how to perform this extended basis set? This we will come in the discussion of next few weeks. See you next week.